Hello. Hi, Hannah. That's because we didn't do them in your notes. We don't need to know them. I mentioned it's kind of funky because of the metals. We're just going to skip over it. I have Twinkie with me. And I have Onyx with me. I'm flanked by dog. Oh shoot. There we go. I see you, buddy. Hopefully we don't have any technical difficulties. I try and do this away from the dogs because sometimes they can be loud. Like that. Red's interested because I'm talking and it's not to him and he's confused. He's a very egocentric dog. And anything that doesn't have priority. So anytime a chain that has a benzene ring kind of hanging off of it, where there's a higher priority functional group somewhere on that chain, like an alcohol or something, you'll name the chain as having a phenyl substituent. Says I'm offline. Hello? Okay. Yeah, Annie, so... Sorry, my dog's being stupid. You're going to call it a phenyl anytime we see it right now. And then on Monday when we talk about other types of benzene rings, you'll learn how to name other things. But right now, it's anytime you have a phenyl, anytime you have a benzene substituent on a chain that has some sort of functional group on it, you'll name it that way. Okay, so Hannah, elimination reaction, 1-bromo, 2-methylpropane. Guys, hold on just a second. I'm sorry. Watch out. Go. Go, go. Go. Alright, sorry about that. I hope nobody gets seasick from having the screen bounce around. Alright. So, 1-bromo. Oh, I know which problem you're talking about. I think it's drawn that way, Anna. And so The question is, how many alpha carbons are there? Well, alpha carbons, so alpha hydrogens. There's only one. There's that guy right there. So there's only one hydrogen that can come off, which means there's only one possible product. We only have to use Zaitsev rule if there's more than one possible hydrogen that can come off. Oh goodness, why is it not? I had the wrong screen on, I'm sorry. It is syncing up, I just had the wrong screen on. Hopefully you can see that now. But there's a longer delay tonight than there normally is. Okay, now I think we might be cooking with fire. Yeah, you can probably see it now. I can see it. I had to pull up the YouTube feed to see what you guys were seeing. Yes, can you deal with Red? He's being a pain. I'm talking to my class. He's outside. Fussing at me, yelling at me. Yeah. Can you just take him upstairs, do you think? Thank you. He just gave you a screw you face. Go, 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 Red. Go, go, go. Yeah, Hannah, sorry. I'll frickin' type it just in case. In case we go offline again with the video feed. It seems like the text is still fine regardless. Well, he was outside and he was still being loud, so anyway. Alright, so Hannah, with the reaction, I showed there's only one hydrogen that is on an alpha carbon. And so that means there's only one product you can get because there's only one type of hydrogen to come off. So the number of alpha carbons is what dictates the number of products. And it's really not just the number of alpha carbons, it's the number of alpha carbons with hydrogens on them. So in the example that I have up there, and let me get rid of some of this because I was just goofing around until you guys started asking me stuff. I didn't realize you couldn't see any of that. Okay, so right here, right, we only have that one alpha carbon. Well, let's say I had a slightly different isomer of that, a different constitutional isomer, where the bromine is at carbon 2 instead of at carbon 1. Okay, so instead of, what was that, 1 bromo 2 methyl propane, this would be 2 bromo 2 methyl propane. So something very similar, right? But in this case, I have a total of 3 alpha carbons, and each of those have 3 hydrogens on them, right? So any of those 3 would have the possibility of deprotonating as part of an elimination reaction, right? So in the case of the molecule here that I put on here, I picked one specifically because it was similar to the other one, but also because if you notice, this molecule's symmetric. It's not going to matter which of those hydrogens we pull off, we'll get the same product, okay? But if it wasn't symmetric, let's say, you know, I had a carbon there, right? I'd have a possible mixture of products because any of those hydrogens could be deprotonated, okay? So, and this is where you're starting to see that in some cases there can be more than one product, and in some cases there's more than one starting material that can give you a specific product, you know what I mean? Hopefully that makes sense. I have spazzing arrows. What are you guys saying? Wow. Well, that's fun. I wonder if I make my box bigger if we can ignore it. Can I just cover it up? That's kind of special. There's a new version of this available. I'm wondering if maybe I should have downloaded it first. The last time I downloaded it right before a session, it had messed up my settings, and so I couldn't stream that night. So I need to download the new version, but I'm kind of afraid to. Let me... There's a little checkbox for capturing the cursor, which normally is good because it means you can see it when I'm on the, like you can watch me, you know, move the cursor around. So like right now you can't see my cursor. But, oh, but that's fun. Okay. I didn't know you could still kind of see what I'm doing even though the cursor's not on there. Well, that'll work. And now we don't have spazzo cursor. We're having a real special night. Here at Dr. Mann's review session, you never know what's going to happen. Okay, so hopefully, Annie, your question is answered about the, what did you want to know? About the phenyl group, and then Anna, and Hannah, hopefully you understand about the alpha carbons with hydrogens on them. If not, ask me to clarify further. Is a dehydrohalogenation a form of an elimination reaction? Yes, it is. So that's actually what this is right here at the bottom. And right here at the top, that's a dehydrohalogenation where you're taking off a hydrogen and a halogen. Right? So in some of these cases, like in this one here, let me just delete some of this. Okay. So in this, oh, Caitlin, yes, I was going to do the mechanism. So in this example here, so like what's happening, right? Well, I have a leaving group that has to leave, and if it is a tertiary carbon, right? Your leaving group leaves first, the same way with an SN1. So you would have an E1 reaction, all right? So if I pull up my error table here, hold on just a second. Okay, so in this case, we'll need to show my bromine. That is not the arrow size that I need. Okay, so bromine leaves. We would get a carbocation intermediate. Something like that, right? And then I'll stick with this carbon that I kind of have highlighted because that would make sense with the product up here. But you would have, you know, the possibility of any alpha hydrogens being pulled off. And so, well, what's going to pull it off, right? Well, we do have a ton of base up here, right? And that's basically it. Yeah, and I mean, we've literally never seen sodium do a single damn thing in this class except be a spectator ion, right? Sodium, lithium, potassium, anything in group 1 and 2, they don't do chemistry in organic chemistry. They're only there, they serve as the spectator ions that balance out our charges, and that's it. And that's not going to change at all the entire semester. Okay, so yeah, it'll be exactly the same. That is like a horrible placement. Let me fix that. Like my hydroxide could use a little help there. There we go. Does that make sense though? Hopefully that makes sense. And if you had an like a less substituted carbon that you're starting off with, so like let's just say you have chloromethane. You know, in this case, because it is, you know, a single carbon, we wouldn't be able to do an elimination reaction, right? You can't do an elimination reaction on something that only has one carbon. You have to have at least two. Whoops, that looked terrible. Let's try that again, okay? So in that case, right, how many alpha hydrogens do we have? We have the 3 right there, right? So in this case, though, the leaving group right there is a primary carbon, right? It's a carbon only attached to one other carbon, which means the mechanism for this one would be just pull that down here. The mechanism for this one would be in the E2 category, where both things kind of are happening at the same time. I want to pull up my... I won't pull up my arrow table. Where is it? I'm going to minimize some screens. Ladies, I am just having, and David if he's here, I'm just having the hardest time with this tonight. There should be a menu bar here for me, for my arrows, and it's disappeared. Well, that's annoying. Okay, let's try it this way then. I'm tired of struggle bussing. I'm going to do it on paint. It is not as glamorous, but yes, David, that is correct. All right. So let's try this. So what I was trying to show is this, where if you have a primary carbon, you'll be able to do the E2 mechanism, where it's all kind of happening in one shot, where you get the deprotonation, the collapsing of the bonds, and then the chlorine, the leaving group popping off, kind of all at the same time. The one before that was more of an E1 mechanism because it was a highly substituted carbon. It was a tertiary carbon. Can you guys see this okay? Hi, Alex. You're a good girl. Kaylee said it's going to sound dumb, but would you show the mechanism? You never have to ask an organic chemist to, will you show us the mechanism? Usually it's, will you please stop showing us the mechanisms? I'm being silly. I'm silly because I love you. Can you have a ketone at the front of a molecule? Okay, so you cannot have a ketone at the front of a molecule. If you have, I feel like I need my pen one. Is this the one that I like? Yeah, okay. So, if I have a molecule with 3 carbonyl groups on it, okay? One of them's a carboxylic acid, one of them's a ketone, one of them is an aldehyde, right? Aldehydes are always going to be a thing. You can't have a ketone at the end because a ketone has to be flanked by 2 carbons or otherwise it's not a ketone. The reason you would know that it's oxo is because when you have oxo, you always have a number on it, right? So in the problem I have here, right, it would be pentanoic acid, I'm sorry, propanoic acid, right? And then I would also, that would be carbon 1 because that would have the highest priority because it's a carboxylic acid. So then I would say 2,3-dioxo. Now, I don't need to know off the top of my head that the oxo is a ketone or an aldehyde because as soon as you write down the parent chain, you'll know propane, 2,3-dioxo, one's a ketone, one's an aldehyde. So it doesn't really double it over like that. Okay, so, right, an aldehyde by definition is at the end, always. Same as a carboxylic acid, it's always at the end. Ketones are not at the end, they're somewhere in the middle. If they're not a ketone. So in this molecule here, because aldehydes have top priority, we would name that as a 3-oxo-butanol, right? If I had this as a hydrogen and an OH there, I would name that as 3-oxopropanoic acid, right? So it's all based off the context. Like, you wouldn't know if I said, that molecule has an oxo group, and if I didn't tell you where, and if I didn't tell you what the parent chain is, you would have absolutely no idea if it was a ketone or aldehyde, but you would know that you have just a plain old carbonyl somewhere. Either an aldehyde or a ketone. Alright. Caitlin wants a nomenclature problem. Draw me... Let's see. Sorry, I don't have all my italics and stuff. Actually, it might work on here. Yeah! Shortcuts work in Microsoft Paint. I didn't know that. Let's see. Let's do R... 2-hydroxy... 2-hydroxypentanal. So I gave you one to draw and one to name. So R2-hydroxypentanal. So the way I like to do these a lot of times, especially if I'm kind of sleepy like I am now, is I like to just draw up my parent chain and start adding stuff to it. And then if I want to, then I can like redraw it and make it pretty with like all the right stereochemistry and everything. So 2-hydroxypentanal. So that's an aldehyde, which by definition has to go at carbon 1. So then everything else will look like that. And so the question is, what's the stereochemistry of the chiral carbon there? If I say it has to be R, then we want the OH followed by this carbon here, and that carbon there. So right now, as it stands, its stereochemistry would be S. So I need to flip 2 groups to fix that, right? So let's redraw it. 1, 2, 3, 4, 5. Got my aldehyde. So if you look here, this is going to be the wrong stereochemistry. So what I can do is basically flip those 2 groups. That's kind of the easiest way I think to do it, but if you want to redraw it in a different way, you absolutely can. Do I have any takers on the one at the bottom? I like being flanked by dogs on a cool fall night, don't you? Oh I think you guys have met Onyx before. Oh my gosh. Maybe light Onyx. Are you guys like there at all? Can you hear me? Can you see me? Kaylee, it's not just you, hun. There's something weird with the streaming tonight. I'm sorry. I agree, Annie. It's octane. 3, 4, 5, 6, 7, 8. Technically octane. Yes. When it's like this, I kind of wonder if there's like a lot of people online or something. Like maybe it freezes up things. I'm not really sure. Octrane. What else? Let's see. So maybe I counted wrong too. 1, 2, 3, 4, 5, 6, 7, 8. So we would have a 2-ene on there somewhere. We have a 4-all because the alcohol would have top priority, right? And then 6-amino, because it would not have priority. What else am I missing? And then a 5-ethyl. Okay, so looks like 6-amino, 5-ethyl, oct-2-ene 4-all. That's a heck of a name. You know, I always thought it was funny that, oh, hold on, I have to like approve one of you. Annie, I think it thinks you were trying to cuss me out or something. It just had to make me approve your messages. It had those in there. So 6-amino, 5-ethyl, octene 4-all. So remember that octane means alkane, A-N-E. Octene means it's a double bond in there. And octine would be a triple bond. So you don't need to put the A-N in there. So it's not octanene, it's just octene because it's, you know, renaming the parent chain as an alkene. Dang it. need to start playing music or something. Hey, Onyx. Onyx! Welcome to the internet, Onyx. Yeah. Get your tongue. My dog's goofy. Ketone and alcohol mean these are in the correct order for priority. Yes, yes they are, Caitlin. I agree. Do we not use sulfuric acid in a hydration reaction? Yes, yes you do. You need it as the catalyst. If we're given a molecule with an alkene and an alkyne, all we do is just redraw it as single bonds and leave benzene alone? Annie, I don't know what you're talking about. Oh, for hydrogenation. Yes, that's correct. When do we not use sulfuric acid in a hydration reaction? All the ones we've done this semester, you'll always use it, Hannah. Kristen, can you be slightly more specific? We went over enantiomers and diastereomers for like 2 weeks. I don't know exactly what you want me to talk about. So Kristen, if you just want like a refresher on enantiomers and diastereomers, that's fine. I would suggest just watching the Khan Academy video on it tonight, if you want a quick refresher on it. Because we obviously aren't going to have time to like recover all of enantiomers and diastereomers and stuff tonight. The one on exam 3 that had us label enantiomers, diastereomers. Well, we didn't do meso compounds this semester. The first one on the 2012 test. I don't have the tests in front of me. That doesn't help me at all, sorry. But those are similar to the problems that we did last semester, or last exam. So you should know how to do those. What exactly do you need help with? So, Caitlin, it is for, like, you can do it with 4 different carbons attached because, here, let me show you. Like, if I have, oh my gosh, there's like dog hair all over me. Okay, so there's only one chiral carbon. Can you guys see this? Okay, you can. There's only one chiral carbon on this molecule. It's this one right here, right? It literally is a quaternary carbon with 4 other carbons attached to it. But those 4 carbons aren't equivalent, right? This is a CH3. This is a CH2CH3. This here is a CH3, CH2, CH2, right? So it's not the same because it's not symmetric, right? So you have to go through and find whichever one has the highest atomic weight first. Well, all of them have carbon, so you have to go to the next one. And if that's carbon, then the next one, so on until you find the highest atomic weight difference. Second carbon from the left, this one. Oh, yeah. If you're talking about this one right here, these are both CH3, so those are exactly the same thing, right? So it wouldn't be chiral. Problem that had R-pentanol. So pentanol, if you have a chiral pentanol, it would have to be at carbon 2. Because carbon 3, it would be in the middle, and you'd have CH2, CH3 on both sides, so it wouldn't be chiral. So what do you want to know about this? Yes, you have. If you're trying to show R or S, you have to show the wedge lines and the dash lines always. That's why I always do it that way. There's no way to show it without doing it that way, unless you're doing Fisher projections, which we didn't get to. So like this molecule here that I have up, you don't know if this is R or S because we haven't specified the direction of any of those atoms. Okay, there's no like three-dimensional orientation because I didn't use the wedge lines and the dashed lines to indicate it. So I have a hydrogen on here, I have a CH3 on here, I have the rest of this thing on there, and the alcohol. So if I wanted to do the easiest way and just kind of pick one, right? So this would have the R stereochemistry, and then I can either flip things or draw the mirror image, right? We talked about doing that. But that would be the S enantiomer. You too, sister. I complicate things as well, my friend. What do you need to know, Kaylee? All that we're doing is adding hydrogen and palladium as a catalyst, and you just get rid of all the double bonds. Like if I have, oh shoot. Like, I mean, it doesn't matter. We could have like a billion double and triple bonds in here. Oh, wait. That's probably hard to see. Yeah, we're not learning any mechanisms for them. That's why there weren't any new notes. might have added too many carbons. Yeah, the mechanism form's kind of funky. Yeah, I definitely added too many. The mechanism form's kind of funky, and I think it's easy enough for us just to say we're not going to need to learn it for this class, so we're not. Yeah. But anyway, that's what it is. It's just you add all the hydrogens wherever you see double bonds and triple bonds. And the kind of important thing for just doing hydrogen and palladium, so it's basically hydrogen gas is what you add in, and because it's a gas, it's very hard to control the quantity, right? Like, because you can't use it on a scale or something. So you basically have to use, like, you can't really selectively say, I just want to add in one equivalent to, you know, only take a alkyne to an alkene. So there are other ways to do that, but we're not learning them in this, in a brief class. In general, you can, I mean, there's different catalysts for this. You could do palladium on carbon. You can do platinum oxide, PTO, platinum 2 oxide. So there's different catalysts out there. The only one we were really working with was the palladium on carbon. I said we could just abbreviate it as palladium, and then that was it. You mean hydroxypentanal? Because you wouldn't name it 2-hydroxypentanol. Okay. Guys, I'm going to mute you for a second. Red's up there with Brandon, whimpering and whining because he's stuck alone in the room with him. And then everything was quiet as they thought. They contemplated life that day. Speaking of stereochemistry, I actually talked to my veterinarian on my way home from work. I had to stop in and get some medicine for Onyx. I love you, Hannah. I love all you guys. But yeah, here, I'll show you something interesting. So, Red has this issue with his bladder, where, for whatever reason, he has trouble controlling the pH of his urine. And, you know, if your urinary pH goes up too high or too low, you can get a couple different problems. But, anyway, there's a chemical that you can buy, it's like more like a dietary supplement than anything, that you can purchase to help with that. I buy it from the veterinarian's office, but it's not, that they consider it a supplement and not like a drug. Well, here's the structure of it. And so this is actually the amino acid. pH imbalance is often caused by UTIs, but it can also create an environment that you're more likely to get infections and stuff. So yeah, but give my dog cranberry juice. Okay, like everything gives red gas. I'm not giving him cranberry juice. It would be terrible. But anyway, so this is actually the amino acid methionine, and the chemical that they, the drug that they give him is called methioform. And I was looking, and it's actually a enantiomeric ratio of the D and L isomers, or basically the R and S isomers. If you remember, I said in the old days they used D and L, and then biochemists kept using them. But yeah, it's like, it's kind of neat. It's just a mixture of the L and the D form of the amino acid methionine, and it helps control their pH of their urine. And I was asking the veterinarian how that works, and he's like, I don't know. I said, well, it's interesting because it's just like the enantiomeric mix, and he's like, I haven't had organic chemistry in years. And so I need to figure out, I need to like read the literature on how this works, because it's strange that it contains 50% of the non-biologically active isomer, right? Like we only use L's, and this one has L and D. Like he shouldn't be able to really metabolize or do anything with the D one. So I just thought that was an interesting organic chemistry, things that happen in your home life. Happens in your home life if you're an organic chemistry professor, I guess. You might pick out things that other people probably wouldn't give a crap about, but I just thought it was interesting, and it's like, I'll share that with my organic class. Okay, so I guess we're probably done. You guys are kind of teetering out, but if you want, you know, you can still ask me questions. You can still email me tonight and get in touch with me if you have anything that you need me to answer. Okay? Close some of the 35 computer programs I have open. You're welcome, Kaylee. Hopefully, I'm sorry that we just had these issues with the streaming today. It seems like it's been good for a few minutes now at least, but oh, here, I can like make me big and talk to you. Here, Twinkie cam. Twinkie! Twinkie! He's got very little legs. They're kind of special. He's a very solid dog. Twinkie's a very solid dog. He's kind of chubby, we can't help it. It's genetic. He's big boned. Anyway. Twinkie! Alright. Well, I'll talk to you guys tomorrow, or if you email me tonight, I'll hit you back up. I usually have been trying to go to bed before 1, so email me before 1. Okay? And I will see you tomorrow. Bye, my wonderful little organic students. I love you all.